Good morning. I selected Aramids as the topic for my graduate student presentation because I work with Aramids, specifically Nomex and Kevlar, at my job at DuPont. I was interested in learning more about the chemical structure and properties of these materials, and I'm looking forward to share what I learned with you. So what are Aramids? Aramids are a class of extremely resilient and heat-resistant synthetic fibers. They have low flammability and chemical resistance to most organic solvents. Aramids also have outstanding mechanical properties, including a high strength to weight ratio and outstanding abrasion resistance, which makes them difficult to cut or fray. These properties make Aramids excellent materials for personal protective equipment, like firefighter or racing uniforms, bulletproof vests, industrial garments, and cut-resistant gloves. The unique properties of Aramids are given by their chemical structure. Aramids are synthetic aromatic polyamides. They are not naturally occurring fibers like cotton or wool, but are manufactured in a lab or industrial plant. They have polar aromatic backbones in which the aromatic monomer units are joined by amide bonds. The aromatic rings and the conjugated amide bonds that link them together are particularly strong and resistant to chemical attack. They also provide a high degree of heat resistance to the polymer backbone. As a result, Aramids do not melt or drip, but merely char when exposed to high temperatures for prolonged periods. The long polymer chains are rigid because the bulky phenyl groups prevent polymer chains from rotating or twisting about their chemical bonds. The ordered nature of Aramids allows close packing of the aromatic polymer chains, which gives Aramids their tough, stiff, high melting characteristics. The most common polyamide synthesis methods for aramid fibers are polycondensation reactions of AA with BB monomers or AB type monomers. In the reaction scheme of AA with BB type monomers, polymers are synthesized by a polycondensation reaction between a diamine and a diacid halide. AB homopolymers are prepared by a head-to-tail reaction, in which a monomer having both an amine and acid group undergoes a polycondensation reaction. Aramid synthesis usually occurs in solution, which provides a liquid medium for the reaction. Some of the most commonly used solvents are listed below. I personally recognize diethylacetamide or dimethylacetamide, DMAC, because it is used at DuPont as a solvent to produce Nomex, which we will discuss further in later slides. There are two important structural variants in aramids prepared by solution polymerization: para-aramids and meta-aramids. Para-aramids are synthesized using a polycondensation reaction of a diamine and a diacid halide in lithium chloride or calcium chloride solvents. Compared to meta-aramids, para-aramids are incredibly strong and have a high degree of crystallinity. A common commercial para-aramid is Kevlar. The para-aramid's high strength and modulus is commonly used as hose reinforcement and ballistic protection. Meta-aramids, on the other hand, are synthesized by reacting a diamine and diacid halide in an amine solvent. Meta-aramids are semicrystalline and have a temperature, chemical, degradation, and abrasion-resistant quality. Nomex is a common commercial aramid produced by DuPont. The semicrystalline nature of Nomex gives it a more textile-like quality while retaining its high temperature properties similar to Kevlar, allowing it to be woven into garments. The properties of Nomex lend it to multiple commercial applications. Because Nomex is a poor conductor and resistant to heat, it can be used for arc flash protection and electrical insulation. It can be woven into a durable fabric and developed into personal protective equipment that provides heat and flame protection and chemical resistance to firefighters and industrial workers. DuPont tests and demonstrates the effectiveness of Nomex garments, flame and heat resistant properties, through a Thermoman demonstration. Thermoman is a life-size mannequin equipped with 122 heat sensors that record temperature changes on the mannequin as it is exposed to temperatures of up to 1200 degrees. A computer then predicts the percentage of second and third degree burns a person in that scenario would have received. So let's take a look.
Record the temperature rise on the surface of the mannequin. The computer calculates the predicted percentage of second and third degree burn injuries a person might suffer under similar conditions. Tests show that with exposure to the same flash fire, a worker dressed in cotton or polyester cotton could suffer combined second and third degree burns over up to 90% of his body. While for a worker protected by Nomex, the potential injury level could be contained to less than half, resulting in a lower degree of burn injury over a smaller body area, and thus substantially increasing his chances of survival and reducing recovery time.
You can see at the end of that video, the cotton garment disintegrates while the Nomex garment is still intact, though discolored. We actually have a Thermoman demonstration unit at our site in Richmond, so I've seen this demonstration in person. It's very cool. So we know aramids are synthesized in solution, but how do they go from a polymer solution to a finished product? Let's review some of the spinning and finishing processes used to manufacture aramids. Polymer in solution is spun into fibers in a spinning process. The spinning process can be wet or dry. In wet spinning, the polymer is dissolved in a solvent at a target concentration. This polymer solution is then extruded under heat if needed and pressured into a liquid coagulation bath. The fibers are combined as yarn, and the yarn is drawn to orient the molecules in the fibers so that it becomes stronger. See in the figure on the left that the rod-like polymers are oriented in the same direction after leaving the spinneret. Dry jet spinning is very similar to wet spinning. However, for some polymers, putting a spinneret into the coagulation bath does not work. Therefore, the dissolved polymer is fed out of the spinneret on an air gap to drive off the solvent and then goes into a coagulation bath to be solidified. Meta-aramids like Nomex are manufactured by wet spinning, while para-aramids like Kevlar are made through a dry jet spinning method. So here's a quick video of what that looks like. The final stages of the spinning process for the coagulated filaments consists of washing, drawing, neutralizing, and drying. Sometimes additional heat treatment is performed to orient the molecular chains in the direction of the fiber axis to increase the ordered arrangement of the intermolecular structure. Additional heat treatment can be done in an oven by convection or through hot rollers with saturated steam. The amount of additional heat treatment determines the crystallinity of the final product. Some fibers undergo crimping prior to drying. Crimp imitates natural fibers such as wool or cotton and increases entanglement with neighboring fibers. The more crimp a fiber has, the better it will hang on to other fibers. Thus, the thinner you can spin the yarn. Each zigzag in the crimp is one more opportunity to get tangled with a neighboring fiber. Depending on a customer's requirements or applications, fibers may undergo additional finishing steps, such as pigment addition or UV treatment. Alternatively, aramid fibers can be cut up and redissolved into solution to generate a pulp that can be used to form paper products. These paper products are often used as insulators or developed into a honeycomb material that is extremely strong and lightweight. Nomex honeycomb sheet structures are found in air crane parts, such as flooring panels, interior walls, storage bins, exterior control surfaces, and even wings. Nomex honeycomb composites are also used in the construction of boats that help provide buoyancy and enhance speed. You may be wondering how much aramids cost. Aramids such as Nomex and Kevlar are present in products you may use regularly at work or home. For example, I wear Nomex coveralls and Kevlar cut-resistant gloves regularly at work. They are not dirt cheap, but reasonably priced for the safety value they provide. Because of their unique properties, aramids are being incorporated into products like backpacks, suitcases, cable reinforcements, and more to improve the strength and lifetime of material without increasing its weight. You can see a few examples in this slide. In conclusion, aramids play a major role in modern safety, transportation, and infrastructure. Aramids manufacturers such as DuPont, Toyobo, and Teijin are continuously researching new applications for aramids and better processes to manufacture aramids more inexpensively. Future developments in aramids will lead to safer PPE, equipment, and travel going forward. Thanks for listening, and feel free to reach out to me with any questions. Thanks, everyone.